Good morning, good morning, good evening, good afternoon. This is Dr. Jenkins. Here we are for the remainder of the muscle chapter. Now, when we met for lecture, we talked about the structure of muscle. We talked about muscle fiber types. So we're going to begin now is with a review of the sliding filament theory, everyone's favorite, right? Now, this is a review. You have had to have had anatomy and physiology up to this point. So I just want you to review this. I'm going to point out the important things that are most important for you to review. All right? So we know that in order for a skeletal muscle to contract, it has to have a nerve impulse. That nerve impulse travels down to the neuromuscular junction, right? The neurotransmitter acetylcholine crosses the synapse into the muscle. That nerve impulse, or another word for nerve impulse, is action potential. That action potential travels down into the muscle, travels into the sarcoplasmic reticulum, which stores calcium. The stimulus of the action potential will cause a release of calcium from the sarcoplasmic reticulum, which then travels deeper into the muscle. Eventually, that calcium will bind to the subunit on actin called troponin. It causes a conformational change to expose tropomyosin. Binds to troponin, causing tropomyosin to bind out of the way. And most importantly, now we have the active sites on actin exposed. Then we'll have cross-bridging. Cross-bridging is when the myosin head reaches up and binds to the active sites on actin. Once we have cross-bridging, when the myosin heads bind to actin, then we have the power stroke. Only then does the myosin head release stored energy, and the actin and myosin slide together to cause shortening of the muscle. Now remember, immediately after that, we had the cross bridge, the power stroke, and then the ATP is going to come over and pull myosin off of actin. But as long as we still have nerve impulses coming into the muscle, steps 5 through 8 will continue. Cross bridge, power stroke, release. Cross bridge, power stroke, release. Each time, the actin and myosin coming further and further together. Eventually, there will no longer be any nerve impulses coming down, and therefore, the calcium will be reclaimed by the sarcoplasmic reticulum, and the actin and myosin will return to their original resting lengths. Here's my little picture that I use when I teach this in anatomy and physiology. Nerve impulse comes down the motor neuron. The neurotransmitter acetylcholine crosses the synapse into the muscle. That nerve impulse or action potential travels deep into the muscle, down the transverse tubules, and into the sarcoplasmic reticulum. The sarcoplasmic reticulum, this blue thing, will release calcium. That calcium travels deep into the muscle. It binds to troponin. It binds to troponin, the yellow thing, which causes a conformational change where the tropomyosin, the orange band, slides out of the way. And now we have the active sites exposed, a little eye on the little dot on the eye, or the olive pit. Then we have cross-bridging. Cross-bridging is when the myosin head comes up and binds to actin. Then we have the power stroke. Myosin head releases stored energy. Actin and myosin slide together. But then a new ATP comes over and pulls myosin off of actin to release the cross bridge. However, if there are still more nerve impulses coming down, then we'll have a cycle of cross bridge, power stroke, release. Cross bridge, power stroke, release. Each time the actin and myosin sliding further and further together. Once there are no longer any nerve impulses coming down, then the actin and myosin recoil back to their original resting length, and the calcium is reclaimed by the SR to be stored for next time. Make sure you review. All right, you can see in your notes, Roman numeral number 4. This is also a review. You know, before, when we were talking about this, we were microscopically into the muscle, right? We were microscopically in the muscle looking at actin and myosin. Well, now we take a step back and we can see the muscle as a whole. We already know the skeletal muscle is made up of bundles called fascicles. Each fascicle is made up of individual muscle fibers. So make sure you review some definitions. The motor unit is one nerve and all the fibers that nerve innervates. This should be a review. A motor neuron is one motor nerve and all the muscle fibers it innervates. This purple motor nerve is innervating 1, 2. That's a small motor unit where one nerve supplies 2 muscle fibers. A larger motor unit might be where one nerve supplies 200 muscle fibers. Larger muscles, like the quadriceps, will have large motor units where each motor neuron innervates hundreds of skeletal muscle fibers. Smaller motor units will be present in the smaller muscles that move our hands, our feet, and our face. Remember the principles that all of these motor units abide by. You can see on your notes, all or none. If we contract a motor unit, either all the muscle fibers it innervates contract, or none contract at all. So if I activate this motor unit 1, both this nerve and this nerve will contract. If that motor nerve supplied 200, either all 200 muscle fibers contract or none contract at all. So within a given motor unit, either all the muscle fibers it innervates contracts or none contract at all. Each motor unit contracts with the same intensity, right? Each muscle fiber contracts with the same intensity, but we can change the overall intensity of a muscle contraction by activating more or less nerves. If I want to contract this muscle medium strength, I may only activate one motor unit. But what if I want to activate this muscle with more intensity? Well, now I activate this motor unit 2. So each individual motor unit contracts with the same intensity, but we can change the overall intensity of a contraction by activating more or less motor units. You can see on your notes there, recruitment of motor units. We recruit small motor units first, and then we can get to large motor units. This is evidence for one piece of evidence why warming up is so beneficial. We recruit small ones first, then large. Okay, make sure you review the overall stages of a skeletal muscle contraction. When we send one nerve impulse, this S is referring to stimulus. When we send one nerve impulse, we're going to have one contraction and then relaxation. So for every one nerve impulse, we have one cycle of all those steps of muscle contraction. Nerve impulse goes down the nerve, crosses into the muscle, goes down to the sarcoplasmic reticulum, releases calcium, calcium binds to the actin, and so forth. One nerve impulse, one stimulus, one contraction, and relax. If we only have one nerve impulse going to a muscle, and we only have one series of contractions, we have what we call a twitch. This is the type of muscle contraction we would need, say, for our eyebrow to close or our eyelash. Eyelid. Why can't I think? It's Friday, everyone. If you have something coming towards your eye, your eyelid will close. Maybe you only need one nerve impulse to cause a quick twitch to close your eyelid, and then you're done, right, to protect your eye. But most muscle contractions are summated. So every muscle contraction has to start with one nerve impulse, one contraction. But then, as we send more and more nerve impulses to the muscle, the effects begin to summate. And that just means that we have one nerve impulse and a contraction, but before that first contraction can lead to relaxation, we send another nerve impulse. So the effects begin to add on to each other. The muscle doesn't get a chance to completely relax before we send another stimulus to start the next contraction. Eventually, we keep sending nerve impulses so quickly that we reach a phase called incomplete tetanus. But that will very quickly lead to that sustained contraction of a skeletal muscle called complete tetanus. This is complete tetanus, smooth contraction. Now, when you go to contract a skeletal muscle, let's say you're picking up a glass of water, these are happening so quickly you don't even realize it. There's a twitch, summation, incomplete tetanus, tetanus. It happens so quickly you don't even realize it. The best example I can give for incomplete tetanus is going in reverse. When you start to lift weights in the gym, say you're doing bench press, you're quickly going to go through all these to get to that sustained contraction of your triceps brachii. But if you keep doing a lot of those reps and your muscles begin to get fatigued, have you ever kind of started to become fatigued and then it almost works backwards? Where even though we're probably sending the same amount of nerve impulses, our muscles just can't handle it, and we start to work backwards, and your muscles start to quiver, and that would be right before you drop the bar. Well, that quivering is a form of that incomplete tetanus, that we do go around it, that we do go through on the initial contraction, but it's just so quick you don't realize it. All right, I know that's a review of the physiology. Review the major parts because you will see some questions because this does relate to kinesiology. All right, so now we're getting to Roman numeral 5, and this refers to our mechanical considerations. Skeletal muscles can have their muscle fibers arranged in different ways. The orbicularis oris. This is a muscle that goes around your mouth. Well, if you look at the fibers go in a circle. And what we find is the arrangement of the muscle fibers, the muscle fiber direction, is structured based on the function. So because when we chew, we need to be able to move our mouth in all sorts of ways, it is beneficial to have this circular arrangement. Excuse me. Sometimes we have a muscle arrangement that is convergent. The pectoralis major is a good example of that. The upper portions of the pectoralis major are a little bit more diagonal in their muscle fiber arrangement, and the ones here towards the middle are more horizontal. And that actually dictates some of the actions, okay? The pectoralis major is actually able to help with shoulder flexion. It is these upper fibers that can help the pec major assist with shoulder flexion. But the part that we think of for the pectoralis major is horizontal adduction, and that comes from these middle parts. Sometimes it's a very simple arrangement, like in the sartorius, where the muscle fibers are just parallel in one direction. Sometimes we have an arrangement where they're bipennate, where some of the half of it goes one diagonal, the other half goes the other. Unipennate is just one form of that, one diagonal. Fusiform is kind of a rounder arrangement. So all sorts. You know, if I gave you matching, be able to match the type with the direction of fibers. Be able to give an example of each type of muscle. Of course, multipennate just has many, many diagonals, not just one or two, but many, 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 like the deltoid. Okay, let's look at one particular muscle. This is the biceps brachii. Well, we can break it down into parts of the muscle. Obviously, we have the muscle belly. At either end is a tendon, correct? Tendons connect muscle to bone. Should be a review, but make sure you know it. In the previous chapter, we talked about ligaments. Ligaments connect bone to bone. But muscle tendons connect muscle to bone. Ligaments, bone to bone. Tendons, muscle to bone. The proximal attachment site is called the origin. Where that tendon inserts on the bone proximally is called the origin in almost every instance. The bony process where the tendon attaches to distally is known as the insertion. I am going to be asking you to know some of these origins and insertions. This happens to be the biceps brachii. One of the origins, the short head of the biceps brachii, is the coracoid process of the scapula, right there. One of the attachments of the insertion is the radial tuberosity on the radius bone. But for now, we're just going to identify the muscle belly in the middle. At either end is a tendon. Where the tendon attaches proximally is the origin. Where it attaches distally is the insertion. Generally, when a muscle contracts, the insertion moves a little bit more up towards the origin. Usually, when a muscle contracts, not always, but usually, it's more of the insertion moving towards the origin. And that's beneficial because in this case, if the origin moves towards the insertion, it's going to raise the forearm. And that's the whole reason why we have the biceps. All right. We talked about lever systems. Because, of course, muscles and bones work together as lever systems. A quick reminder, which lever system is utilized by most skeletal muscles? Third class lever. Which lever system provides the best mechanical advantage? Second. That's a review. All right. So now we're going to start to get into more of the specifics, right? There's a lot of different loads acting on a muscle. Now, I'm never going to ask you to draw this, but I do want to make some points, okay? And the first point is there are multiple loads acting on a muscle. The job of the muscle, so here we're trying to, what this is trying to show you is the act of a bicep curl. This person's trying to bring this arm up. The job of the muscle, in this case, the biceps brachii, the job of the muscle is to counteract all the other forces to allow this motion to occur. In order for this muscle, when it contracts, to pull up the forearm, the force of the biceps brachii must be greater than the torque created by the elbow. In order to successfully raise the forearm, the biceps brachii must contract with enough force to be able to overcome the weight of the forearm and hand. The biceps brachii has to be able to overcome the weight of the object being held in the hand. There's a lot of forces that are actually pulling down. There's a weight of this object. There's the weight of the forearm. There's a torque, rotary force around the elbow. So I'm making 2 points here. There are many forces acting in and around a joint and a muscle. There's a weight force, sometimes of body segments or of objects you're holding. There's a rotary force or a torque. So there's many forces acting on the muscle and joint. Point number 1. Point number 2 is that it is the job of the muscle to overcome all those forces. In order to successfully perform a bicep curl, the biceps brachii must contract with enough strength to overcome all the other arrows. If it doesn't have enough strength to overcome those, then it would not be able to lift the forearm. That's all I'm saying there, my friends. Okay, we have already introduced torque. Now we're going to get a little bit more specific looking at torque. We've already given a basic definition A torque is a force that rotates things, rotary effect of a force, rotary force, force that turns things. And when we're talking about forces and loads, we're not going to only be considering the strength of a muscle contraction or the strength needed to lift a certain load. That's part of it. So we do have to measure force, but we also have to measure the direction and distance of that force around the axis. And let's face it, most of our actions are not just singular in plane. A lot of them, most actions in the real world, most actions in athletics are multiplanar, and therefore, even if it's not an obvious example, the obvious example of torque I gave you was unscrewing a wrench. Well, that's an obvious example of rotary force, but even if it's not obvious, because most of our motions are multiplanar, there is some rotation happening somewhere, and therefore there is some torque happening somewhere. Okay, so we're first going to define torque again, a force that turns or rotates things. We're going to remind ourselves that, even if we don't necessarily see it in an obvious way, because most of our actions are multiplanar, there's more than likely some sort of rotary force or torque happening everywhere, somewhere. When we measure torque, we not only have to consider the force of contraction, but we also have to consider distance and direction. Okay, so here's an example of the most common lever system we use in our body when we attach muscles to bones. Think about a bicep curl, okay? The axis is at one end. In this case, the elbow is the axis. The axis is going to be a joint. The load is at the other end that you're trying to lift, because, of course, in a third-class lever, the effort or muscle force is in the middle. Now, you might look at this and say, well, it's not directly in the middle. Well, no, if I draw a line between the fulcrum and the load, the effort is not directly in the middle. But the effort is still in the middle, it's just more over here. But it's still a lever system. Compared to the axis and the load, the effort of the muscle, where the tendon attaches, is still between them. It's not in the direct middle, but it's still between them. Okay. You can see in your notes here some other comments about torque. I've already added that it's not only a measure of force, it's also a measure of the direction and distance of that force, and that's what relates to rotation. You can see letter C there. More torque around an axis results in more rotation. The more torque I can develop, the more rotation I can get. In muscles, these are the two ways that we produce torque. We produce torque, right? Torque is the product of, we produce torque by how forcefully we contract that muscle and the length of the effort arm, the distance and the direction of that force. Length of effort arm and also the direction of the force. I also want to remind you that the unit that we're going to be using for torque is Newton meters. In the US, it's foot-pounds. We're going to use Newton meters. All right, so I have some examples here, and I'm never going to ask you the specific number, but I want to just give you some examples of torque and talk about some examples of torque in the body. One of the best examples where we can actually see it with our naked eye would be a baseball pitch. You know, a lot of people think about the shoulder being so worn down by pitching, and to be fair, a baseball pitcher, softball pitcher too, but a baseball pitcher, does put a lot of force and stress on their shoulder. But actually, there's more force relative to the structure at the elbow. The amount of torque at the elbow that's generated during this cocking phase. So he's cocking back because in the next phase, he's going to push this forward to release the ball. This is a rotary force. It's not just a force in one direction. A force without rotation might be like a shot put. Now, I know in the Olympics, people doing the shot put, they do twists with their body beforehand in their like pre-cocking phase. But when they actually push out the weight, they're doing it just straight forward. They're pushing out the shot put in a straightforward direction with not really any rotation. When we add rotation, we can generate more force, we can generate spin, we can do all sorts of things. So, the elbow generates a lot of that rotary force. 64 Newton meters is a lot, considering how small the elbow is. You know, to give a real life example, we can look at a car. In a car, you can talk about the horsepower. In a car, you can talk about the horsepower, but you can also talk about the torque. And they'll usually say foot-pounds of torque in a car. Power is one thing, right? In a car, power means ultimately you can go X miles per hour. But torque, how quickly can you rotate those pistons to get the engine going? How quickly can you rotate out of a turn and get going? Look, the Ford Mustang Cobra generates 480 Newton meters. So what that's telling, I'm not going to ask you these numbers, but look, I mean, a big engine. And then our elbow generates 1/8 of that? That's pretty cool. So what are some things that we can do to maximize torque? Now that we understand what torque is, rotary force, we understand the benefits of torque. It allows us in many ways to generate more force. It allows us to add a lot of spin and other cool things. So in a baseball pitcher, because they're able to cock back so much and then release that potential energy going this way, it acts kind of like a slingshot. So by adding this rotary cocking back this way, it's like we're really loading a rubber band. So when we want to, we release it and we can generate more force. To really maximize torque, what are some things you can do? I don't think this is in your notes here, but I would like you to add it. Some things you can do to maximize torque. We can lengthen one of the lever arms. The longer this lever arm, the more force and torque you can generate. This is why a taller pitcher, think about Randy Johnson back in the day, right? A longer arm means you can generate more force and more torque. Same thing with a screwdriver trying to unscrew something or using a screwdriver to take off the lid of a paint can. The longer the screwdriver, the more torque and force you can generate. So we can increase torque and force. We can increase torque by lengthening the effort arm, the resistance arm, lengthening the lever arm, and we can increase the radius of rotation. The more that a pitcher rotates their trunk means the more they can rotate their elbow. More rotation means more torque. So 2 things we can do to maximize torque. Lengthen the lever arm, increase radius of rotation. I think these things are pretty common sense, right? Here's an example in tennis, right? The more that Roger Federer twists back, both in his trunk and the more he twists back this way, so more radius of rotation. And tennis players want to hit the ball when their arm is the straightest. Because when their arm is the straightest, that's when it's longest. Some other things to consider. Sometimes there can be different angles of pull. P-U-L-L. I know I say that funny because I'm from the Mid-Atlantic, whatever. The most amount of torque can be produced at whatever joint angle most force can be produced. It's usually mid-range. So what we're saying is, for example, Clayton Kershaw here, he wants to have his elbow flexed to about 90 degrees because 90 degrees is a great angle of pull for the biceps muscle. You don't want that muscle to be too contracted. We don't want his elbow to be too bent. Or we don't want the elbow to be too extended. Most of the time, the muscle is going to be able to produce most force at mid-range. And that means that in order to generate the most force and most torque, you want to have that muscle in mid-range, not fully contracted or flexed, not fully extended or relaxed. And you can also produce the most torque. Just some things for you to chew on, right? I've used this before, like a wrench. Great example of a real-life torque. The longer the arm, the more torque you can produce. The more rotation you apply, the more torque you can produce. I gave the example of cars. Cars utilize torque to spin the crankshaft, which then moves the wheels. Really cool. I already gave you some examples just because it's kind of cool. We can not only can we measure horsepower or force, we can also measure torque. One way to think about torque is the potential for power. It's kind of interesting. Okay, so here we go. Letter D here, muscle group coordination. When muscles work, they work in concert with each other. They work in coordination with each other. And this should be a review. I've hoped you had this in anatomy and physiology or some other course that you've had. So let's say that we're talking about a leg extension exercise. Leg extension exercise. Or if you're not familiar with things in the gym, kicking a soccer ball. But you can't really read that, can you? Let's do black. So think about a leg extension in the gym or kicking a soccer ball. At the knee, the primary motion happening is extension. When I kick that ball, my knee is initially flexed and I extend it to kick. The agonist is the muscle doing the action. Right? The agonist, sometimes called prime mover, the agonist is the muscle doing the action. What muscle is contracting to extend my leg? Quadriceps. Sometimes you have synergists, which are helper muscles. Usually it's not just one muscle creating a movement, there's more than one. The agonist is the primary mover, the biggest muscle, the muscle that's generating the most force for that movement. And then we'll have some helper muscles that are also doing knee extension here, but maybe aren't as big, right? And then we have the antagonist. This is the opposing muscle group that relaxes. Opposing muscle that relaxes. Let's really think about this. If I'm kicking a soccer ball and I need to extend up my knee, I'm going to contract my quads. If I contract my quads and the hamstrings at the same time, what's the overall result going to be? There's a net movement of nothing. It's a stalemate. The quads are trying to extend at my knee and the hamstrings are trying to flex at my knee. So if sets of opposing muscles contract at the same time, the result is nothing. They'll be contracting, but there's no movement because they're both fighting in opposite directions. So in order to successfully extend, I need to contract my quads, but I need to relax the opposing muscle group. By relaxing the opposing muscle group, I let the primary mover do its job. For a given motion, the opposing muscle that relaxes is called the antagonist. For a given motion, the muscle that relaxes is called the antagonist. And this might change. So let's give another example. This was an example of knee extension. Now let's switch gears. Let's talk about a leg curl. A leg curl, the motion occurring is flexion at the knee. Okay? So doing a leg curl, now we're talking about flexion at the knee. So what does the agonist become? Here, the agonist is the hamstring, because they're the ones that cause flexion at the knee. What is the antagonist going to be? Now, if I want to contract the hamstrings to flex at the knee, I have to relax the quads. Maybe a helper for knee flexion is the sartorius. It's a smaller muscle that can also act to help in knee flexion. Maybe it's the gastrocnemius that can also help with knee flexion. Do you see what I'm saying? The more examples you can do with this, the better. Let's say I'm doing a bicep curl. In a bicep curl, the joint motion occurring is elbow flexion. What is the prime mover or agonist? Well, the biceps. If I want the biceps brachii to contract to cause elbow flexion, I want to relax the opposing muscle group or the triceps. So the triceps becomes the antagonist. A helper muscle that also does elbow flexion might be the brachialis or the brachioradialis. Okay? Now, agonist, synergist, antagonist. Then we have stabilizer. A stabilizer is something that contracts to stabilize. It's oftentimes core muscles. Think about the soccer kick example. In order for me to kick a soccer ball, I have to make sure that my abdominals are contracted a little bit to hold my trunk upright, or else I would fall over. So a lot of times we have abdominals or back muscles that act to stabilize. A stabilizer supports the body or often maintains posture. Supports or maintains posture. The neutralizer is a muscle that contracts. A neutralizer is a muscle that contracts to prevent an undesired motion. A neutralizer is a muscle that contracts to prevent an undesired motion. This tends to be a harder one, but we're just going to keep practicing it. If I think about the first example here, leg extension or kicking a soccer ball, I don't want any hip abduction. So you see in this one, I've given the muscle that's contracting to be a neutralizer and what motion is trying to prevent. When I'm doing a soccer ball, when I'm kicking a soccer ball, I don't want crazy amounts of abduction at my hip. I want to abduct a little bit, but I don't want to do it too much. So I might actually be contracting my hip adductors as a way to keep my hip in towards my body. What about the example of the bicep curl? Usually when doing a bicep curl, you want to keep your elbow at your side, right? So what motion is keeping your elbow at your side? Shoulder adduction. I'm trying to prevent abduction because I want to perform the bicep curl with my elbow at my side. So we think about what are some muscles that do adduction at the shoulder? Pec major. So even though you may not realize it, your pec major might be contracting a little to prevent that undesired motion. We're going to be doing this and giving examples in lab. This requires knowledge of the muscles, which I expect you to have of the major muscle groups, right? Okay. Now, the rest of this chapter, we have to talk about some miscellaneous things. I think what I'm going to do is I'm going to break this up into 2 videos, just because it'll be easier. So this will be the last topic for this first video. And then when we come back, the second video will be much shorter. So I alluded to this before, but here we're giving it an official name. So you should be aware of, in terms of muscles, something called the length-tension relationship. And what this is telling us is muscle contractions are strongest in mid range of motion, in middle range of motion. So we're looking at the relationship between how much force can be produced on the y-axis to the length of the muscle. Easiest example is to think about the arm and forearm. So imagine we're looking here at the elbow. I'm considering drawing the elbow, but it's not going to look so good. Yeah, so we have a person, right? And then we have a person's biceps brachii attaches to the shoulder and then attaches here to the radius. Okay? Doing a bicep curl, he'd want to flex his elbow up that way, right? So if we look at the angle between the arm, here's the elbow, and the forearm. If I extend my forearm, this is 180 degrees, right? Straight line. So my biceps brachii doesn't have as much force capability when fully extended, right? So when my elbow is fully extended, do it yourself while you're sitting here, right, or standing. When you fully extend your elbow and you try and contract your biceps while keeping your elbow straight, you can't produce as much force. The other side of things is true. What if I'm contracting already, right? So here my biceps is, my elbow is already contracted fully. With my elbow contracted fully, flexed fully, I can't contract it much more either. So muscles are strongest when they're in their mid-range. If you flex your elbow too much, your biceps muscle is already close together. So the actin and the myosin are already really close together. If my elbow is fully extended, the muscle might look more like this. Now the actin and myosin are too far apart. Here, the actin and myosin are too close together, so there's nowhere for them to go to slide past each other. Here, they're too far apart, so it's actually harder for the actin and myosin to cross bridge. So when in mid-range, The actin and myosin are perfectly aligned. They're not too far apart. They're not too close together. We can cross bridge and power stroke, and we can therefore generate the most force. Muscle contractions are strongest in the middle of the range of motion. Why? Because the actin and myosin are not too far apart. They're not too close together. The actin and myosin are optimally aligned. All right, so we'll end this first video there, and then we're going to come back for the second half.